Thank you so much for the introduction and for having me. It's a pleasure to be here. And yeah, as you see, I'll be talking about three things about polynomials, but they really comes out of the study of a problem that I talked about in Princeton 2 days ago. Joint work with Shaoming from UW Medicine and Wang from UCLA. So for those of you who weren't at the talk, I won't have as much of motivation, but I'll try to recall what happened in the talk, and hopefully these three things are interesting in their own rights to everyone. So hopefully I can entertain you a little bit by themselves. And if you have questions, just feel free to ask. And here's the rough landscape of the talk. And yeah, so as you see, these things came up in the study of rmander type operators, and some of them are even before our work. So some of them are by other people, and we just did our own part in this part of research. And we have this Bergen's condition. We made a conjecture about rmander type operators that obey this condition. And we have very strong evidences on it. So I'll talk about what those are. And the three things, I'll motivate them each. I guess the second and the third are both with very strong geometric intuitions. So I almost had my title about 0 sets of the polynomials, but the first thing is a little more algebraic and a little difficult to motivate if you just say it from the beginning. So I guess my way will be try to motivate each of the things and then tell you what the theorem is. Some are by other people, some are by ours, and they will be related. So as you see, we will have both negative results and positive results. And this first thing, Kakeya compression, comes from the study of the negative results. And I should say that this work is a natural extension of the 1991 paper by Bergen, not the more famous paper, but also quite impactful, the LP boundedness of rmander type operators. And he focused in the 3-dimensional case. We looked into the higher dimensional case and also revisited the 3-dimensional case. And we also had some positive results. And I'm going to tell you 2 key ingredients. In the proof of those positive results, there are also significant technical parts that I wouldn't able to tell you, but I'll focus around these 2 ingredients, which are, as I said, are interesting in their own rights: polynomial Wolf axioms and the so-called brooms and the variety uncertainty principle, which you can see as a very baby case of the fractal uncertainty principle that Alex just talked about. So very baby case, you will have bounded degree 0 sets of polynomials, so very special fractals. But I think that's an interesting theorem on its own. Okay, so let me start by a brief recap of what happened on Monday. So again, if you weren't at Monday's talk, I'm sorry, I will just have time to review the framework of our study and people's study. So rmander brought up the notion of a type of operators called rmander type operators. So very general oscillatory integral operators from n-1 real variables to n variables. You can study things locally, so this also works for manifolds, but you can focus on the Euclidean space setting. And you have a particular way to rescale your real phase and your cutoff. So cutoff, it's not a big deal, but the real phase, you give it a larger and larger oscillation by lambda. So you form a family of operators t to the lambda, and lambda goes to infinity. You want to study their the big space mapping properties. So that's the setup. And you need to have curvature conditions to have interesting results for that. So those are open conditions, and rmander set it up in the following way. So you need the mixed partial derivative of x and c to have rank n-1 throughout the support of the cutoff function. And in this way, you can define the Gauss map as a wedge product of each partial cj of gradient x. If you can compare, so the classical Fourier restriction operator is one example of this kind of operator. You can check in that setting. and the Gauss map will boil down to the Gauss map for the hypersurface. That's why it's called the Gauss map. In the variable coefficient case, you have another explanation where this hypersurface will change with x. So you define it as a Gauss map, and you take the Hessian along this certain direction. So this is sort of the nth direction that is special, like all the other direction will have linear terms in C, and there's one direction in the x variable because x has one more dimension than C that wouldn't see the linear term of C, and you're interested in the Hessian in this direction. So hopefully it won't be degenerate. You want the determinant to be not equal to 0. So as the first step of studying this kind of operators. Once we have this, then you have a family of Polynomial type operators with lambda going to infinity. And motivated by, for example, restriction and Bochner-Ries, you're really interested in the boundedness of this family of operators, this setting, and Polynomial even asked whether they will be bounded as if you were in the restriction or the Bochner-Ries setting, at least in the conjectural range. So, but it's actually not the case. So I talked about some counterexamples. In all dimensions greater than 2, it is the case for dimension 2. So that actually in higher dimensions, things start to behave differently. And I talked about people finding, adding positive curvature condition to the whole world can help things behave better a little bit, eliminating some of the worst possible operators in this large class. So the positive curvature condition says that you have this Hessian. It's not only non-degenerate, non-zero determinant, but it's also always positive definite on the support of A. So your implicit hypersurface would have principal curvatures always the same sign. That's the positive curvature condition. And people realize that the bilinear method works quite well in the positive curvature condition setting to give improved results, starting with Lee's result in 2006 in 3 dimensions. But it turns out that in all dimensions higher than 2, again, you have counterexamples which prevents you to have everything in this class behaving as well as you would expect in Fourier restriction and Bochner-Ries. So what's the next step? Well, we thought about it, and actually Bergen thought it way ahead of us about 30 years ago in 3 dimensions. So Bergen had a condition, and we thought a very direct analog. It seems to be a good generalization into higher dimensions. So I need a bit of setup to state it. And I also talked about it in Princeton. So for this phi, you can do diffeomorphisms in X and in C respectively, not jointly. So you wouldn't ruin the structure of the problem in this way. And then you can change this phi to the so-called normal form around the point. So you can send the point to 0, 0, and you can do some nonlinear change of variables to eliminate certain terms in the Taylor expansion of phi around 0, 0. So you see what I meant a minute ago. You have n-1 variables, each coupled with a C variable, and then the nth variable with a quadratic form in C. So the curvature condition amounts to say that this capital A as a matrix in dimensions at least 2, at least 3. I mean, in 2 dimensions, it's just a number. Is going to be non-degenerate. The positive curvature condition just means A is positive definite, and then you find certain terms missing here. And Bergen studied this in 3 dimensions, and he showed that you have to have this thing as a necessary condition. Otherwise, your operator will stop to be bounded on LP when P is greater than something that's greater than 3. So you cannot go all the way down to 3, which is the conjectural range in Fourier restriction and Bochner-Ries. So you have to have this everywhere. And we did use analysis for geometry to prove that this condition is intrinsic. If this is multiple at 0, it doesn't matter which diffeomorphisms you take in the beginning, like it will always be obeyed. So this condition is also suitable in higher dimensions, as we predict. So once your phi satisfies this condition everywhere, we predict the behavior of the operator should behave should be as good as that in restriction and in boundaries. And our evidence is, I think, comes next. So yeah, we had this conjecture. If you satisfy the positive curvature condition and a Bergen's condition, then you should have LP to LP boundedness for n p greater than this threshold that you see in Fourier restriction and boundaries, which I also talked about in Princeton. And our results regarding this conjecture to support it are a negative one and a positive one. So our result says, the first negative result says, if Bergen's condition ever fails at a point, then this boundedness stops working for p below certain number, which is not very important, but the important thing is that it's not quite at the conjectural threshold for Fourier restriction or boundaries. So once p goes below this threshold, the LP boundedness just stops working. So there's a strong evidence, at least it shows that Bergen's condition is going to be necessary for a conjectural LP to LP boundedness holding in this restriction range. And we also prove a positive result.
Why do you say generic failure?
Generic because it's like this condition is a closed condition. So yeah. In other words, if this condition is not satisfied, you have an open set of phase functions. So it will fail for everything that open.
Amongst those, only generic.
Sorry.
So amongst those, it will fail. If
yeah.
this condition is not met.
Yeah, if this condition is not met at any point, then the LP boundary is in the restriction range will fail. Yeah, that's why it's called generic failure. Yeah. And back to our positive results. So in the other direction, we prove that if Bergen's condition is satisfied anywhere in the support of A, then you do have positive results. I don't want to talk about the explicit exponent because it's kind of technical to get, but the important thing is that this exponent improves the currently best known range of exponents in both boundaries and Fourier restriction in all sufficiently high dimensions, and it's an asymptotic improvement. So you can have partial results where those conjectures hold for exponents greater than 2 plus a constant over n, and you can ask about how large that constant is. So it's not made to 2 yet, and people are trying to push it down, and we push it down further better than the previous I guess best result by Jonathan Hickman and Josh Zhao, I think. For the Fourier restriction, and we did reproduce that with Changgen O, Shaoming Guo, Shukun Wu, and Hong Wang for boundaries. But this is an evidence that this conjecture might be plausible. At least it captures all the most state-of-art techniques. Like, in other words, we can study boundaries and Fourier. We can study this more general conjecture without talking about boundaries or Fourier restriction in this generality, and we still get the best results for those two particular conjectures in sufficiently high dimensions. So, for those of you who know more, I should say that our theorem, this result, the exponent matches Hong Wang's exponent in 3 dimensions of 3 plus 3/13. So there's a recent development improving Hong's bound by Shukun Wu and Hong Wang. But I'm kind of optimistic that the method here could probably adapt to their method as well. But their method is kind of technical, so haven't looked enough into it. And so those are the results that I talked about on Monday, and yeah, so I plan to tell you a bit about interesting things to me that happened in the proof that are presentable. So in order to do that, I need to do a bit of preparations. So let me start by recalling the framework of studying Fourier restriction. So this is a recently developed, so actually there's a recently developed framework that's based on a more classical thing called the wave packet decomposition. So unfortunately, I didn't have enough time to draw the pictures here, so I have to draw it on the board here. So apologies to the remote audiences. And here I'm going to draw a picture for a lot of things in this slides. So you have the C space here and X space here. So if you're talking about Fourier restriction, you will have a Fourier space here and the physical space here, but slightly different setups here. And then you care about what the operator T to the lambda would take some function XT2. So the way you think about it, because of the existence of the cutoff function, you look at the effect of T to the lambda on a large ball of radius lambda. Here, lambda is a large constant that goes to infinity in the X space, that's n-dimensional. And in the C space, you focus around like approximately the unit ball. That's how the rescaling would work for you. And as harmonic analysis, a natural thing is to decompose in the C space. You decompose the C space into caps. So as Dominic also mentioned in his talk, this is more of the classical setting because the curvature is non-vanishing. And each cap, we call it lambda to -1/2 cap. It's just something of radius lambda to the -1/2. It's like a square of radius lambda to the -1/2. And now you can look at the contribution from each cap. And the contribution from each cap will be roughly constant. So this is a manifestation of the uncertainty principle plus some elementary differential geometry. You will see that you would have constant magnitude on tubes. They might be straight, they might be curved, that are known as wave packets. So these are of thickness lambda to 1/2. And thanks to a comment that Alan made to me on Monday, I'm going to have it like added here for Bochner-Ritz. So tubes are straight in Fourier restriction and in Bochner-Ritz, and they correspond to the so-called Kakeya and Nicodemus setting, respectively.
I'm sorry, what's the mathematical definition of the uncertainty principle that you mentioned?
Yeah, that's a great question. Thanks. So the uncertainty principle I mainly have in mind is when a function having its Fourier support in some ellipsoid or box, then this function has to concentrate not much beyond the dual box of it and its translations. So for example, in one dimension, if the function whose Fourier transform is inside the unit line segment, then the function itself should behave roughly like a constant in any unit interval. So this can be made rigorous in various ways, but that's one way to describe it intuitively. Does this answer your question?
Yes, thanks.
Okay, good. Okay, so you will just know that in those two problems, positions and directions distribute differently. And our 5 people paper actually did a transformation that's called pseudo-conformal transformation to Bochner-Ritz. And it turns out that under that transformation, the wave packets line up very similarly to those in Fourier restriction, and that enabled us to apply more tools in Fourier restriction to Bochner-Ritz. And in general, I should say that the wave packets, they develop along polynomial curves, so they don't have to be straight. But if you're waiting to lose the power of lambda here, epsilon's power of lambda here, so you can assume their core curve is like a polynomial curve by Taylor expansion. And one last thing that's good to have in mind is that you have a structure to induct on scales, meaning that if you look at a ball whose radius is capital R, inside this ball of capital radius lambda, then you have a similar decomposition of T to the lambda F inside this ball, so colored in red. That's also good to keep in mind, and the wave packets inside this red ball would be thinner of thickness R to the 1/2. So this is the framework of wave packet decomposition. This back at least to Fetterman and Cordova's work to localize things both in physical space and the frequency space. And Bergen actually made a lot of adaptation to it to give new results, for example, on Fourier restriction using the Kakeya results. More recently, there's a rapidly developing technique called polynomial partitioning. And actually, it first arose in incidence geometry problems like Kakeya over finite fields. And like, so a lot of things inspire this. And I believe Alex just talked about one aspect of this method in a quite different context. But roughly speaking, this polynomial partitioning is a way to study this T to the lambda f by cutting up the function repeatedly using zero sets of polynomials. So let me see if I have, I should draw the tubes thinner so that they behave really like lines or finite degree curves. So if you have wave packets like this, then what you do is you cut up the function evenly and then cut further inside each part, and then in this way you decompose your function evenly. So I think this this picture is probably and what's the advantage of using zero sets of polynomials to cut up the space? Well, the tubes are relatively thin compared to the whole scale lambda. They have thickness lambda to the 1/2. And one advantage is the quite algebraic reason. So if you pretend the wave packets are lines, then a line cannot intersect the zero set of a polynomial more than the degree of the polynomial. But on the other hand, if you have a degree D polynomial, you can cut up the space evenly into D square pieces thanks to this polynomial partitioning technique by Fuss and Katz. Actually, they first brought up the idea of polynomial partitioning in the study of Erdős distance problem over the plane. So like you can use this to cut up the function evenly and see the non-overlapping of wave packets in this way. And one thing you should pay attention is that if you pretend wave packets are straight lines, then it does happen if you when your zero set of the polynomial passes through these lines. So like you actually have things to worry about, and that's why I put the last remark here. One cares a lot about possible tubes near the zero set of your polynomial, and that's the short introduction I'm going to give about the polynomial partitioning. And so I'll as I said, next up I'll be talking about 3 ingredients in the proof, in our proof of both negative and positive results, and hopefully you get some intuition of those. I cannot fully tell you about the connection and how they're proved, but I'll choose the most intuitive part. So here we go. First about the negative results. And we have these negative results. The result that if Bergen's condition fails at some point, then the LP boundedness stops working for P less than a threshold above 2n over n minus 1. And some numerology, so the threshold for 3 dimensions is 40/13, not quite matching the positive results in Fourier restriction, but still kind of significant. And the previous result by Bergen, we improved it slightly because we were able to optimize certain things, taking a slightly different viewpoint than his. And this is proof, as in my title, by Kakeya compression. Is there a question?
Oh yeah, why does this exponent agree with Wang's exponent?
No, it doesn't. It doesn't.
Does it?
No. Her exponent is 42/13. Yeah, I mean, the dream would be if you have a positive result for this. This would be very nice because you know a gap. Like I actually conjecture there should be gaps for different type of operators, maybe based on their Taylor expansion, but that's very speculative. Like people's positive results are not strong enough to match this, or our result is not strong enough to match this. But yeah, but I think I do think there could be very interesting results in the full truth, but I don't know. Yeah. Okay, so this is proved by Kakeya compression. What does it mean? Well, we have one way. So if we want to prove negative results, then one way to prove it, because we want to prove it for p greater than 2, the idea is that we know a lot about L2. So both by Princeton and by kinking. So you can have different contributions line up, and then you do a kinching, a random argument without seeing the exact value. You do have a square root cancellation thing, which gives you large LP norm when p is greater than 2, when things are focused around smaller sets. So one idea, which I'm sure dates back to at least Bergen in his 1991 the paper about Kakeya and restriction, is to make this thing concentrate as much as we can in this pool of radius lambda. And for each cap, what's the best you can do? You can concentrate things all on one wave packet, meaning that you can assume everything else, every other wave packet gives negligible contribution. And then this seems to be a way to get the function concentrated. And then you face the question of packing all the wave packets from different C into a small set. So this is conjectured to be impossible in the Kakeya world. And that's one big motivation of studying Kakeya for harmonic analysis people, because it rules out this particular scenario. But in the general world, especially for when the Bergen's condition fails, at least Bergen knew this in his 1991 paper when he studied a three-dimensional case. The idea is try to compress part of all wave packets from all C into a small region, and then just use kinching. So not necessarily, strictly speaking, not all C, but definitely an n-1 dimensional set of C. So this is kind of intuitive. You have an n-1 dimensional degree of freedom, and each one gives you a tube. So if you were lining them up randomly, they will pack into an n-dimensional thing. But now, Bergen in his 1991 paper is saying that if this condition is ever violated, you can pack it into a two-dimensional thing in 3 dimensions. So that's where he got the negative result. And one thing to first think about is to compress all the core curves as in the Kakeya needle setting. So you have wave packets to compress. You can ignore the thickness first and then first put the core curves together. But you do need to, in the end, care about the slightly thicker version of the tubes. And you do this by caring about the surface area. So I don't know if I'm going to talk about that part today, but we do need that in the proof. Yeah, and the other remark is that in Bergen's work, in our work, we didn't use the whole length of the wave packets. We chose some certain shorter segments on them, and this allows us to do a Taylor approximation to simplify the problem. That's why you don't see higher derivatives in Bergen's paper, but for our paper it's the same, but the argument I would say is a lot more involved. So I guess to be even more precise, well, before that, showing you the only paper I was the only picture I was able to squeeze in this talk before my laptop was out of power. So this is a visualization that's in the paper by Largos, Johnson Hickman, and Marina Iliopoulos, where they prove the worst possible operators with the positive curvature assumption can behave very badly, and they need this Kakeya compression as well because they're proving negative results in that section. And for one phase function, you see this kind of Kakeya compression phenomenon. Everything is going near a two-dimensional surface in 3 dimensions. So that's a nice picture. And what do we do in mathematical rigorous terms? Well, back to this normal form, and because we need to state Bergen's condition, let's transform things to normal form near the origin, and then assume Bergen's condition fails at the origin. So what's the basic setup? My apologies for having to draw a picture again. So you can actually capture the information of the wave packets in a quite accurate way. So for each C, if you look at the core curve, corresponding to the cap containing C. You can choose the position parameter, which we're going to call omega, so we'll continue to call it omega of C. So what does that mean? Well, once you choose this omega, you can draw the whole core curve. So it's convenient to set up t, like the time, in the n dimensions. So xn equals to t. So I should specify that. Sorry for not specifying it. But then you can denote the rescaled core curve to be x of t, t. So x of t is an n-dimensional thing, and then you can look at it in different t. And x of t, what does it satisfy? It solves a very specific equation. So when you take the gradient in C of phi, so I should say that little x, I'm missing this one, sorry, little x equals to x of t solves this equation. So maybe I'll put it down here as well. Solves so you have the initial hyperplane, and you choose your position of the wave packets and or the core curves of the wave packets, and you can draw a lot of curves. You try to put them into a smaller region, maybe around n-1 dimensional hybrid surface for an n-1 dimensional set of C. So this is not easy to do, but you can do this in Bergen setting, and in our setting we slightly uses a different method. So here's more about what's good in this in order to rigorously prove the Kakeya compression. And this is definitely known by Bergen. And we also use this. So it turns out that you can look at the union of these curves slicewisely. You can fix the time t. So now it's a map from n-1 dimensional variable to another n-1 dimensional variable. So you can do some calculus to compute the volume of the image. It's that simple. So you just want to make the determinant of gradient C xt small. And that's going to be about the first thing I tell you about polynomials. So maybe not very easy to motivate, but that's going to be our goal. And in order to, as I said, there's a remark that eventually you have to go from the union of curves to the union of tubes, and you have to consider the surface area because the union of tubes is just a neighborhood of the union of curves. So you need to consider the surface area. This is controlled by noticing everything has bounded degree and use the semi-algebraic geometry. So I'm not going to talk about that. But in the three-dimensional world, actually it turns out to be more intuitive. Once you have this determinant really small, so Bergen was able to even show this intuitively that all the core curves can concentrate near a two surface. More accurately, once you fix this time t, they have to all have positions near a line. So this line will vary from time t. So that's a root surface, at least in 3 dimensions. We're not doing this because it's already tedious enough to make this very small. So we just focused on very abstract considerations, and we don't know if how they will concentrate it. We just computed the determinant. This is actually a very useful tool, as you'll see in the second part as well. And okay, so yeah.
Okay, so you have your wave packets, and they're compressing near some surface.
Yes.
And you're saying that out of this construction, you get the compressing near some world surface. Can you write down ahead of time what world surface they're going to compress on, or will it somehow, after you compute your choices, you'll get some world surface, but you don't know ahead of time what it's going to be?
I guess for Bergen's setting, you can write this down by hand, like he did it explicitly by solving some very specific equations. Also, the error term he needs, you're going to see it here, is probably cubic. So he only needs to see the quadratic terms. Yeah, for the higher dimensional case, I don't know if our construction will make it concentrated around hybrid surface yet. It's a good thing to look into, but yeah, I don't have much geometric intuition. And also, Bergen and later one studied a lot about the quadratic phase. I think certain terms are quadratic, and then you have the geometry of things. And for the worst possible operators, I think you always have the biggest possible Kakeya compression, and you have the geometry of those two. You can probably look at the 3 people's paper to see some worst possible Kakeya compression. Yeah, but for different operators, you have to analyze it case by case. And
do you know if like will compression always happen near a real surface, or could you arrange compression near?
Oh, that's a great question. I don't know. I don't know. Yeah. So the question is, are things always close to a ruled surface? I guess ruled surface is more of a thing in 3 dimensions, right? In higher dimensions, there might be surfaces ruled by higher dimensional objects. So I don't know how strong they will be. It will be interesting to think about. Yeah. Okay. So more rigorously, all you need to do is to prove this lemma. It turns out to be enough for the negative result, but it's only one more power saving than the trivial result. So once you have Bergen's condition fails, remembering that's that's a condition about 2 certain coefficients in the Taylor expansion. They are not proportional to each other. So 2 matrices not proportional to each other. Once this happens, we can find the position function. So it doesn't make sense if I were to just give you this lemma as the first thing from the beginning, but hopefully I already have a bit of motivation for it. So once you have this condition fails at the origin in this normal form, you can find, of course, you can make it polynomial because everything would be correct up to order of error. But we can find the polynomial omega with omega 0 equals to 0, such that if you have all the core curves solving the position constraint, then you look at this determinant, you find that it is made unusually small. And this will be enough for the negative result. You still need to compute it because, as I said, you can only compress part of the curve, not the whole thing. So it's not clear before computation whether you can have a gain or not. As I remind you, the trivial bound here, by taking all the omega equals to 0, for those of you familiar with Kakeya, this amounts to saying putting all the tubes passing through the origin. So you don't really do anything in the Kakeya setting, as you can imagine. Taking omega equals to 0 doesn't give you anything in this setting either. But for it gives you the trivial bound that is n-1's order. So we're saying that once Bergen's condition fails, this is important. Otherwise, we have the positive result to prevent this lemma holding. Then we can choose omega carefully such that the order is actually n. So this is the more technical of the 3, and I won't be able to explain the proof to you, but a few comments about the proof only. So again, this determinant is n-1 by n-1. So in 3 dimensions, it's 2 by 2. And one key idea that you have to do to obtain this somewhat counterintuitive is that, so if you recall the case when you take omega to be constantly equal to 0, then this determinant of the Jacobian, when you compute it, doesn't have constant term. So automatically you have degree n-1. But this is not a good thing to do. If you want to have a higher order of vanishing, you have to choose the constant term. So if you look at the linear algebra question, you see it real quick. And you do need to choose the non-zero constant terms to start, and in 3-dimensional case, this is done by Bergen. In higher dimensional case, this actually gave us a lot of trouble because, for example, when the dimension is 101, you have a 100 by 100 matrix that has some sort of constant term, and you want this order to be like 101. So initially I thought maybe this is impossible, but somewhat we did this by a mixture of changing of variables and some linear algebra, maybe Jordan canonical form sort of trick. But in the end, we proved this in the whole strength that you can do this. So I just say it's done by very involved linear algebra. Okay, so any questions before I go to the positive results? And also, how long do I have? Just want to make sure.
5:30.
5:30. Okay. Okay. So yeah.
What does the inner product of T and C mean?
What does the
inner product, like the parentheses of O? Sorry, that's not inner product.
which one?
The O of notation.
Oh, I see. This is a vector. I just you can see the value of t plus the value of c. Yeah. Also, I should specify x of n is equal to t. So sorry for the typo here. Okay, so back to some interesting things in the positive results. Well, the first thing I would like to talk about is polynomial of axioms. So it's not very interesting to it's not very intuitive to start from our own results, but this result itself is something I like a lot. So I'll first tell you the polynomial of axioms in Fourier restriction. So as I motivated a while ago, it's important in Fourier restriction to care about tubes near the zero set of a polynomial. Because what would happen if all the wave packets are near the zero set of your polynomial? The polynomial partitioning will be very weak there. And Larry Goose had the framework of studying those tubes individually and had a question just about possible directions of tubes in the neighborhood of a polynomial. And this was answered by himself in 3 dimensions. And this was an open question for quite some time, and then proved in 4 dimensions by Josh Zhao, and roughly at the same time in all dimensions by Neskes and Keith Rogers. So Josh's proof has more geometry and is more involved, and Katz and Rogers' proof is more concise, and that's what I'll be talking about for the most. So let's digest this theorem. I really like it a lot. So unfortunately, I have to maybe let me draw more pictures here. So you have the zero set of a polynomial, and the polynomial has bounded degree. So the degree is bounded by a constant. I'm drawing a hyperplane to show you the degree 1 example. And assuming you're taking a neighborhood of its zero set, and the neighborhood has thickness that I set up as delta here. So thickness delta or constant times delta. And you take this inside the unit ball. So everything is inside the unit ball. You try to fit in a couple of delta tubes inside this neighborhood, or you can slightly thicken the neighborhood by constant times, but so to avoid stupid constraints. But the highlight is that you might squeeze in a lot of delta tubes, but the number of directions you're able to squeeze in that are delta separated is kind of very much smaller than all the number of directions. So all the maximum possible delta separated directions in n dimensions is like delta to the minus n minus 1, but you can only have delta to the minus n minus 2 here. So, and plus some epsilon, which we don't really care too much, and which probably can be removed. So, but because we don't care about it too much, I'm not going to talk about it. So the important thing is that this constant only depends on the dimension and the degree. So you're allowed to have polynomial, because in the polynomial method, like a sort of disadvantage of it is that you use algebraic topology to tell you there exists some polynomial with zeros that does this, but you don't really know what it is. You have no idea, like you have very little information about it. And you allow, for example, for your polynomial to have curvature depending on delta. So you will start to see very strange zero sets and their neighborhoods. But this is a universal bound, and it's actually quite strong. And I'll just say one word of how to use it in Fourier restriction. Basically, one scenario is that when you start off, all your wave packets are around the zero set of polynomial. With this theorem, you'll see there are very few directions, meaning that there are very few caps of C contributing. So in this way, you see a gain from L2 to L infinity, which is very important if you are out of the classical Stein-Thomas range. And one trivial thing that you can do that you will fail is that if you just start by counting the total number of tubes and then try to bound this thing by the total number, then you will fail, because there can be a lot of tubes in one direction, just like this hyperplane case. So you cannot do that. But very magically, this theorem tells you, even though there can be much more tubes, the number of directions are actually the correct bound you can get. So you also have this theorem for other dimensional algebraic or semi-algebraic sets, but this is already an interesting enough thing. And a few words about how Katz and Rogers proved this in the full generality, and a few other things I feel quite interesting to talk about. So yeah.
Can you just say what, this may be a tangent, but you said these are polynomial Wolf axioms. What are the Wolf axioms?
Oh yeah, so the Wolf axioms are about things around subspaces, not the zero set of polynomials, to my knowledge. And polynomial Wolf axioms are named in that way because you have zero sets of polynomials.
So like, is Wolf axioms like a degree 1 version?
Yeah, I think that's right. Yes. And Wolf had this when he studied Ruixiang and Kakeya, and he didn't have access to polynomial method back then. So yeah. Okay, so it's worth mentioning one word about Kakeya conjecture, which didn't make into this talk so far. And very roughly speaking, the conjecture says that straight delta tubes in different delta separated directions almost don't overlap. So if you take the union, you will see a full dimensional thing. That's the conjecture, and it's verified, for example, over finite fields and over other local fields like the Q of P. So quite interesting developments and strong evidences. And to study this conjecture, you can assume all the tubes roughly pointing up. Like this is already an interesting positive portion of all the directions. And then you can define the Kakeya map. And again, taking the upper direction to be T direction, then you can take the direction C. So a Kakeya set contains a line segment in each direction. If this direction is roughly pointing up, but then for each direction, you locate one line segment, and then you pin down the initial position of that line segment. In this way, you can construct a set that contains a lot of lines, and then you can determine how large it is. So it's convenient to talk about this Kakeya map from the direction to the initial position when t equals 0. And very roughly, I can explain the idea of proving the polynomial Wolf axiom to you in this way. So very remarkably, if you start off with such a neighborhood, as I said, for each tube, for each direction, there might be a lot of positions of the tube inside here. But it turns out that you can choose a very nice position in a very nice way, actually a semi-algebraic way. You can actually make the Kakeya map not only with part of the directions, a subset of the directions, but you can make this map semi-algebraic with bounded complexity because you start off with something of bounded complexity. So that's a very nice feature of this polynomial Wolf axiom. And the key ingredient is by Tarski-Seidenberg, quite deep theorem in real algebra geometry. And because it's semi-algebraic with bounded complexity, you can roughly say that it's almost smooth. So this can be made rigorous by, they did make this rigorous by almost lemma, but I'm sure there are probably other ways to do it. And then you can compute the Jacobian, again, the Jacobian on each slice as we did before. And you can lower bound the volume. Kakeya said if the Jacobian on average is larger than constant, then you do have this very strong theorem. And one nice feature about this Jacobian computation and the argument is that you do the Jacobian, you switch the integration order between t and the x prime. And then when you integrate over t, you suddenly find yourself having a polynomial that's monic because it comes from a determinant and has bounded degree. And then you use the fact that the average of that, no matter what other coefficients are, it's going to be greater than a constant. The unit interval is elementary, but very useful. It's the last step of it. And one related thing, actually two, I would like to tell you is that actually this might sound very strong, but it is proved that Kakeya is known if you have a Kakeya map that is has certain Holder continuities. Even true for Lipschitz Kakeya maps, like as a simple corollary. This is proved by Yu Fu and Shaoming around 2020. And the method, as I understand it, is kind of related to this proof of polynomial Wolf axioms. And one more remarkable recent breakthrough that's only tangentially related to the topic here is by Wang and Josh Zhao that I think maybe was just posted 1 or 2 months ago, is that this Kakeya is also true in 3 dimensions of much interest for the so-called sticky Kakeya maps. And sticky, I just want to say that it's much stronger than Lipschitz because sticky allows the 0 measure Kakeya sets. And this result, I think, doesn't allow 0 measure Kakeya sets. And the Perron tree construction, if you know it, is going to be sticky. So that's a very nice recent result. I think they requires more ingredient from, for example, additive things like Bergen's theorem that the reals doesn't have half-dimensional subrings. It's all related to that. Yeah. So I still yet to understand it, but
very few people understand.
Yeah. Okay. So this is the proof sketch, and just one word about what we did. We did sort of the variable case. Then Bergen's condition is satisfied, and very nicely it comes out like in the right place when we're trying to prove this polynomial Wolf axiom. So we proved there's a version for polynomial Wolf axiom if this condition is satisfied everywhere. We also proved a stronger version that's also used in the study of restriction with a lot of scales independently by Hickman, Rogers, and myself, and George Stahl in 2019. This also continues forward. And the one thing is that you can do a Taylor approximation and assume everything is semi-algebraic. You probably lose the exact Bergen's condition, but it holds up to some order, and that's enough because you're allowed to lose a lambda to the epsilon. And I'll just see where this condition comes in. It naturally makes the difference when you compute the Jacobian. And when you switch the order of integration, you see that trick again, and you can comfortably use this again. So you have to see the proof, and the Bergen's condition is no more, no less used there. So that's the polynomial Wolf axiom I had in mind. And the final ingredient I have is the so-called variety uncertainty principle. And I probably will not talk too much about this slide. This is just some background. So this has to do with the Broom approach by Wang to give this 42/13. That's an improvement over Larry Goode's result of 3.25 back in 2014. So very roughly speaking, what this is this is about a hypothetically enemy scenario. In this scenario, you cannot improve Larry's result. But in this scenario, wave packets add up to functions that concentrate on standard sets. You will have to see this if you go to the detail of the polynomial math partitioning. But this forces you to have many wave packets lining up in a special way. So I apologize for drawing more pictures, but the Broom thing will roughly look like this. So you see that they have to be away from each other when you move away from time equals to 0. And you use the 2nth argument to relate the things at time equals to 0 to time equals to lambda. You see the Brooms don't meet a lot, so you will have an improvement. So only a very vague intuition I can tell you about Brooms. It's very technically complicated. Yes.
How is this different from a bush?
How is this different from a bush? Well, they also line up in very special way. For example, in 3 dimensions, you can have them all lying on the plane. Yeah, so this is one kind of bush, I guess. Yeah. And we thought about from the time of improving the estimate. So I'll just state the key ingredient there. So which we call a variety uncertainty principle, which is the fractal uncertainty principle in the case where things are bounded degree and are bounded at 0 sets of bounded degree polynomials. And as we learned from Alex, we should exclude the case where you have lines perpendicular to each other, for example, in 2 dimensions. So my setup sort of prevents this from happening, and I'm going to show you by drawing one more picture. So you can actually state this in the Fourier transform setting: physical space on the left, Fourier space on the right, and you have the 0 set of a bounded degree polynomial on the Fourier space, another 0 set of the bounded degree polynomial on the physical space. You take suitable neighborhoods of them each. So I guess what did I use? I used the 1 over capital R and little r, I think. So okay, I'll use y1 has neighborhood little r, so little r neighborhood of this thing, and 1 over capital R neighborhood on the Fourier side. And one key thing is that I only take part of the hybrid surface so that the tangent plane everywhere has angle roughly very small constant angle against the horizontal hybrid plane. So this rules out the two perpendicular line situation, for example. And then you have, once the Fourier support of F is in this second set, you know the L2 norm of F on the first set has a power saving that's almost the optimal you can have. So that's the advantage of having this setting. You have a really strong conclusion. I won't go through this, but I just say that it's used by an observation that's related to pseudo-conformal transformation. So the Fourier transform here is not the Fourier transform you see in the setup of Fourier restrictions, so for example, but not too much on this. But maybe one comment on this theorem is that we don't know an elementary proof. It's very tempting to think about an elementary proof and removing this epsilon. So we weren't able to achieve this. Instead, we proved this by induction on scales. So repeatedly using L2 decoupling or L2 orthogonality, I should say. And we use a geometric lemma of Larry-Guth. So I thought it would be interesting to introduce that lemma. So that will be my last slide. This lemma also very nice. And you don't need to worry about the constant. So the setup is you have a polynomial of constant degree in n dimensions, assuming the zero set is smooth, not a big deal. And you take the set of points whose tangent plane has angle roughly 1 against the vertical axis. Then if you take a unit cylinder and you intersect it with the zero set for this part, it can be covered by constant many unit balls. So once the zero set goes like almost horizontally, the part inside the unit cylinder can be covered by constant many balls. And I should say that the key point of previous variety uncertainty principle and this theorem is that your constant is the same game. Your constant is only allowed to depend on degree. It's not going to be allowed to depend on the zero set of the polynomial. So that increases the difficulty of the proof. For example, your polynomial, I mean, they might go roughly horizontally, but they might have really large curvature, like really small circles, for example. This you need to take into account. And if you integrate by parts, some things might blow up. So that's why we had to use this geometric theorem. And this theorem, again, this theorem is not completely trivial. It's proved by differential geometry and integral geometry. It has more general versions. We need more general versions, but the proof is entirely analogous. And one last interesting I'm going to tell you is that it came up originally in a very different place when Larry studied the Fourier restriction. So glad to use it again in another part. And I guess that will be my talk. And thank you so much.
Good, wonderful talk. Any question? Comment?
Yeah, I have one. Is there perhaps a reason why you spend a good portion of the talk outlining the proofs instead of actually saying what they are?
No, because I told him to.
Sorry, the question is why did I arrange the talk in this way?
Yeah, more or less. Like, why not just say what they are?
I guess I just wanted to talk about some motivations. I will be happy to share my slides. So if you want to see the more technical parts towards the end, I will be happy to share it.
But was the Princeton talk the same or was it different?
Yeah, the Princeton talk was mainly about the motivations and the history. So for example, I talked a lot about the counterexamples and who made which discovery, which I omitted. Yeah.
Okay, thanks.
Sure. Yeah, what's your question?
Oh yeah, so this theorem, seems to suggest that you're using the fact that these are varieties and not just, smooth curves in some important way. Do you expect this variety uncertainty principle to be true if you replace them by smooth curves with the same condition, or do you really need them to be varieties?
That would be an interesting question. Like if you want to replace the question is what will happen if you replace varieties by smooth curves, right?
Yeah.
I don't know, like that will be a good thing to look at. But for example, our count, like the Ruixiang Zhang principle in our version, the constant definitely depends on the degree. So if you just do a Taylor approximation, it will blow up. But
what if you do this? Take cube, that breaks everything. Right?
Yeah, that's
So
one.
suddenly need polynomial.
That is one way to force you needing the polynomial. You can take a lot of the union of a lot of for example, lines. But that you can, I mean, if you rule it out just by taking one single curve or one single hyperplane, the first thing I would be to see how this proof works in that setting. But I don't know for now out of my head.
Wait, I'm thinking, why doesn't the angle condition make that not happen?
Why does sorry?
Like I would have thought that the angle condition
Yes.
would mean that you can't have something like this.
Because the polynomial has a bounded degree. So for example, one simple thing you can have is to have its intersection with the horizontal lines.
It's like if you go like this, then your angle has to go point down at some point.
Yeah, and you delete that part. So
Yeah, that
this is
condition is only for a
where
subset.
Oh,
yeah, so you allow small circles, for example, but you're only taking part of it.
I see.
And that's needed because we have a polynomial, we have a zero set, we don't know where it lies, but we can break it into finitely many parts and deal with them like one by one. And once that's, we can do that. So we need to take care of those pieces, and also we are allowed to consider a version like that. Yeah.
You mentioned integral geometry. What do
yes.
you mean by that?
Yeah, so one example would be Crofton's formula. So Crofton's formula is like if you take a hypersurface of bounded degree inside the unit cylinder, infinite unit cylinder, it might have infinite surface measure because it might go all the way down. But if you look at its projection counting multiplicity to the bottom, then you immediately get a finite number. So this is roughly seen by intersecting this hypersurface with vertical lines, and each vertical line would have a few intersection points. And if you do the projection, that will count the projection when you do the integral. So things like that, very, very basic. I think Larry just used one thing similar to what I said. Yeah. So no fancy integral geometry here. Yeah.
So in this proof of the variety uncertainty principle, is the geometric lemma the only place you use that these things are zero sets of polynomials?
So it's a geometric.
Like, is the only place that you use polynomials in this proof?
Yes.
Is geometric lemma?
Yes, I will say that. Yeah, and yeah.
So
This is the only place where we need the polynomials and bounded degrees. Yeah. Right.
So like
you probably can generalize this to other hypersurfaces or varieties satisfying this. Yes. Yes.
Do you always consider polynomials of bounded degree, or are there cases where the degree could depend on, like, for example, delta to the minus epsilon?
And that's a good question. So thanks. Do we always use polynomials of bounded degree? I think it's a trend now, and partially because of the polynomial wall of axiom. So for this polynomial wall of axiom, if you try to track the constant, then that constant is probably double exponential indeed. So I would mostly avoid using polynomials of degree r to the epsilon, but if I were to force to, I would think more about their properties. They are much harder to understand than the bounded degree polynomials, mainly because of real algebra geometry or minimal geometry when you have to use it. Yeah.
When Alan asked this question, I think you said brooms are a special kind of bush.
Yeah, that's one way of me
Right.
understanding it.
So let me ask a different question. What's the bush that's not a broom?
What's
What's a bush that's not a broom?
What's a bush that's not a
Like an example of a bush that's not a broom.
well, you can draw it arbitrarily, I would
Like
say.
the full bush.
Well, full bush, you can say maybe it's composed of different brooms, but yeah, well, I mean, generically, I would say it's not. Like
Okay.
you choose the directions randomly, you choose the collection of directions randomly. I'm not going to get much structure out of it.
So what's the structure in the definition?
Yeah, I mean, one key
Something having
structure is
separated-
it has to spread out in a way here, but I should also say that in our new result in higher dimensions, we really didn't use much of the geometry, and that's what made brooms really more flexible. So for example, in the three-dimensional setting, I probably didn't see this. I didn't say this either in the three-dimensional setting. It's easier because you can take one variety to be just a line in 3 dimensions. It's 2-dimensional versus 2-dimensional in her application. But once you're in a line, this becomes trivial, and you can remove the epsilon because it's planetary. So yeah, this is one way to make brooms more flexible, and that's what we did. Yeah.
Perhaps say in a couple of words, where's the epsilon loss and the exponent in the Katz Rogers?
In the, oh, I see. Yeah, that's a great question. So as I said, I think I believe if one works hard enough, you can probably remove this epsilon. So I can explain to you where this comes from. So in order to study this in a really concrete way, they approximate semi-algebra sets with bounded complexity by images of smooth functions. So that's a lemma of Gromov. So totally non-trivial lemma, but they just borrowed it. And then because of that, they need to do a Taylor expansion and a Taylor approximation. So it's a common technique that you allow an epsilon loss, and then you take a polynomial of degree like 1 over epsilon, but that's still a constant. So you lose a constant that depends on epsilon, but that's totally okay. So that's a common technique now, I think. Like they definitely use it. But if you don't do the approximation, I see no reason like by only working in real algebra geometry to get some results that says this. But I definitely haven't looked into this in full details, but I thought maybe one can remove the epsilon if you're interested in this for some other motivations. But we are happy to apply this with an epsilon loss, of course. Yeah.
All right, well, I think that ends a wonderful day. Let's thank all the speakers.